In this video, we're going to look at position vectors, and the position vector of a particle is given by r of t, which is x of ti plus y of tj, where I and j are unit vectors in the x and y directions. It's also called a vector function of the scalar real variable t. T is a parameter, often represented as time. If we can eliminate the parameter from these two equations, so-called parametric equations, we can obtain what's called the parametric equation of the parametric form, which is the explicit or the equation of the path. Sometimes we can't find an explicit relationship, but an implicit relationship of the form. Either way, this is the Cartesian of the equation of the path. Also, we might want to carefully consider the domain of the values of t, which often specify the domain and function of the variables concerned here. Sometimes we might want to find the closest approach. We might need to find the position vector or the Cartesian coordinates of a particle at a given time, or, for example, when the particle is closest to the origin. Okay, let's have a look at our first example. A particle moves so that its position vector is given by r of t equals 4t minus 3i plus 3t minus 1j for t greater than or equal to 0. A couple of things we want to find here. We first of all want to find the distance of the particle from the origin when t equals 3. Then we want to find part B, the general formula for the distance of the particle from the origin at any time t, and then the closest distance of the particle from the origin. Okay, so let's do this on a calculator page or a calculator application. So I'll press the on key and press the calculator page. Now, to do this, I'm going to define the x and y coordinates at a general particular time. So menu, actions, define. We're going to define it as x1 of t equal to 4t minus 3, and also define y1 of t. So once again, we go menu, actions, define, y1 of t equal to 3t minus 1. I'm going to store both of these as a position vector. Although we normally use the notation i's and j's, we can represent these as a matrix form, and the matrix is a matrix of one row and two columns. We can get that from the template next to the little book. So there it is. Use the arrows to scroll across. So I've got a 1 by 2 matrix there. In the first one, I'll enter x1 of t. Don't press enter, tab or right arrow to the next field and enter y1 of t. Now I want to store this one to r of t. Whether I use define x1 of t equals or define a function or store, all of these have the same basic functionality to store. So I'll go control var, which is going to store that to r of t. Okay, so to simply find the coordinates when t equals 3, all I have to do now is I can press the var command, or I can press r and substitute in t equals 3. So that'll give me, 4 3s are 12, minus 3 is 9, and 8. So x is 9 and y is 8. Now I want to find the distance of that vector, or the magnitude of that vector. So we do that by finding norm. So we'll go menu, matrices and vectors, and come down to option number 7, which is norm. So all I have to do is press norm and press up arrow twice. So the norm of r of 3 is going to give me the square root of 145. Now if you think about that, that's just 9 squared plus 8 squared, which is 81 plus 64, which is the square root of 145. So that's correct. All right, so that's the distance of the particle from the origin at time t equals 3. Let's find the general formula for the distance of the particle at any time t. Well, let's just type in r of t. And that's obviously x of 4t minus 3, 3t minus 1. So now we want the norm of that. So rather than typing it from the menus, I can just press up arrow twice and now change that 3 to a t. So that'll give me the distance of the particle from the origin at a general time t. Now, if I want the closest approach then, I have to find the derivative of that. So we want to find when the derivative is equal to 0. Note that that applies for both a maximum and a minimum. So again, from the template next to the book command, let's find the derivative of that function. So we want d by dt of that function. So let's just press up arrow to grab it. We don't need to type all these things in again. And if I want to solve that when it's equal to 0, we'll go Menu, Algebra, Solve. Once again, just press up arrow and solve that equal to 0 for t. So that gives me the time when we're closest to the origin. So let's find the coordinates of that one by entering r at 3/5. And once again, we'll now find the magnitude, or to find the magnitude, we use the norm of the vector, and that will give me the distance of the closest approach. So the distance is 1. Now we can visually see this if we go to a graphs page. So let me press the on key again and go to a graphs page. Now it's expecting a function, so let's just press Menu and change the graph entry edit to parametric. And the whole point of defining x1 and y1 is that the graphs page automatically knows about these. So when I press enter, we will see the particle travels along a straight line. When t equals 0, x is -3 and y is -1, so it starts at the point x equals, -3 and y equals -1. So to prove that it is in fact a closest distance, a minimum, let's press Menu and do a trace of this function. And just pressing the arrows, we can see that when t equals 0.6, which is 3/5, it is closest to the origin and moving further away from the origin. Okay, so that's a very nice little example illustrating position vectors and the norm, which is finding the magnitude of a vector.